just move on to our last presentation from Nicholas Harvey from Harvey Rock Physics. It's about stress tensor computation from Borehole images. So, Nicholas, here you are. The stage is yours, and
okay.
I look forward.
Thank you. Yeah. So, like Andrew, I was kind of asked to fill in the gap. So I suggested to him that I could talk about the quantification of the orientation of maximum stress field using borehole images and open hole logs. This presentation will kind of walk you through the process and show a couple of examples from some work that we're shortly going to be publishing. So basically what we do is we take the wireline data and we use that to quantify the rock moduli, the UCS strength. But when we combine it with the acoustic televiewer data, we can also get an idea of the maximum horizontal stress orientation. And through synthesis, the what are known as the principal stress orientations and magnitudes. And since the audience is mainly oil field based, there is a difference between the horizontal stress minimum and maximum that we sort of know, and the vertical stress. In mining and in civil engineering, they use what they call the principal stress orientations and magnitude. And basically they call them sigma 1, sigma 2, and sigma 3, sigma 1 being the maximum. And it doesn't really matter what the orientation of that is, it's kind of always the maximum. So for us, it was an interesting journey to learn about this kind of difference between the way we sort of look at things in kind of petroleum and the way that they look at things in sort of other industries. So the methodology that we take is kind of more geared for coal and mining sort of community. But basically, we load the full wave sonic and the density data. We take the acoustic televiewer data and impute a stress ratio into our computations. We do a petrophysical analysis, which gives us clay content porosity, lithology, and comparison with the lithologic information that they have. And then we have a geomechanical model that's based on work that was done with the drill bit company that allows us to recompute the sonic and density. We can determine lithostatic stress, the elastic moduli. We can calculate the static moduli, and we can calculate the maximum and minimum horizontal stress, pore pressure gradient, and fracture initiation pressure. The latter two are not so important in the sort of industries that we've done this work in. And once we get that information, we integrate the borehole derived orientation with the mechanical properties, and we compute the sigma 1, 2, and 3. And this gives us a quantification of the stress tensor, and in their eyes, the maximum and minimum tensor, maximum minimum orientations, vector orientations within the stress tensor. And finally, we take the information, and if we do a number of boreholes, we calculate, we present it as maps and stress magnitudes by formation. The stress magnitudes are done as gradients. Now, all of you probably know this information. The acoustic televiewer is a tool that measures two properties: time of flight and amplitude. And the measurement that most people are particularly keen on for interpretation is usually the amplitude image, because you can use that for doing picks and so on. The time of flight is relegated to calculating radii and for using for casing integrity. But in the sort of work that we found that the information gives you a very high resolution caliper, and you can actually see dilation in the borehole, and you can actually use that to represent the maximum minimum horizontal stress directions. And here's kind of a stylized example of what we're talking about. As with the other presentations, as soon as you see breakout, you get kind of this ovalization. And the maximum horizontal stress orientation is generally considered to be the minimum diameter. One of the reasons why we like the transit time is that it will give us variations to within less than a millimeter. And the sort of data sets that we're working with, which boreholes that are around 4 inches in diameter, we get variations down to less than a millimeter from the borehole televiewers that we're using. The other part of the exercise is usually the incorporation of the density. And again, this information's probably familiar to this audience here. But the density is a quantitative measurement that's based on high energy gamma rays emitted from a cesium source. And through Compton backscattering, we get an electron density, which we convert to an average, which we convert to a bulk density. On the other side, we look at the full wave sonic, and we use that to get the compression and the shear. And the sort of tools that we deal with, we can have 2, 3, 4, or even 8 receivers for the tools that are capable of logging in for a whole 4-inch diameter holes or smaller. The computed results that we sort of deal with, and the ones that are sort of most important to us, are the ones at the top. The sonic, Poisson's ratio, both static and dynamic, and the Young's modulus. But we also compute a whole variety of other things, which are of interest in mining and civil engineering as well, particularly the ECS, particularly the CCS. They are also interested in such things as brittleness, and somewhere in there is a measurement that gives us the wear factor, which drill bit wear factor, which is also of interest. And finally, we have the vertical stress and the 2 horizontal stress components that we compute. So, and this is kind of where the magic begins. We sort of synthesize the stress magnitudes with the computed orientations from the borehole images, and this allows us to, through a series of tensor optimization calculations, produce the orientation of sigma 1, sigma 2, and sigma 3. And when we when we synthesize this, we get the principal stress magnitudes. And in terms of an output, this is kind of what we produce. So here we have the maximum horizontal stress orientation, and this is calculated from the transit time image from the borehole image. And we plot it as a polar plot and also as a continuous vertical curve. The reason we plot it as a continuous vertical curve is that we're able to illustrate to people that we're getting a continuous profile, not just one point. And the reason that's important is that you start to see variations or changes in stress orientation that are associated in changes in lithology and the intersection with faults and other sort of things. We also compute the ratio of the minimum to maximum, which is this curve here. And then we compute the rot moduli, and we present those, and we present the Poisson's ratio, both static and dynamic, and then Young's modulus, static and dynamic. And over here we have the horizontal and vertical stress magnitudes, and we have the sigma 1, sigma 2, sigma 3 calculated, which we present here. And these are calculated based on a TVD depth. So we're capable of handling deviated boreholes as well. And that's one of the things in mining, is a lot of these holes are deviated, so they intersect roughly orthogonal to the bedding. I don't know how many people are aware, but there are techniques that allow you to actually measure the stress in situ. One of them is overcoring. There's the SIGRA method, and there's also CSIRO. Collectively, there are 2D, which allow you to just get the orientation. And then there are 3D, which allow you to get an idea of the orientation and the magnitude. And we've kind of worked with both. And this is an example of the SIGRA approach. And the triangles are the SIGRA points. And again, this is point. And then we have the vertical stress, maximum horizontal stress orientation that we've calculated. Over here, you can see a problem that they have in mining, which is the same as in the oil field with artifacts. The drillers in mining are more than keen to get to their target depth. And so we can end up with a lot of perturbations and effects on the transit time information, which produces wobbles and other impacts like this. And whilst we're able to accommodating most of the centralization issues, we can't accommodate a good driller, that's for sure. And we will always get these effects. So if I and I skipped over this because this is the actual principal stress computation. So we present all the information. Typically, we present the fracture aperture and the fracture orientation, because these can be orthogonal to the maximum stress. The dip can be orthogonal, and the strike can be in the same direction as the maximum stress, and there can be some relationship between them. So we present that. We do the horizontal stress, and then the principal stresses. We have sigma 1, which is blue, sigma 2, which is red, and sigma 3, which is green. The reason we chose sigma 2 as red is when you're dealing with an extensional or a normal faulted regime, sigma 2 is usually the maximum horizontal stress, but in this case, we're actually looking, well, in this example, it is an extensional regime, but when I get to the examples that I have, they are reverse fault examples, so they're different. So what we find is that the sigma 1 azimuth orientation is always the same as the horizontal orientation, and sigma 2 and sigma 3 are orthogonal to that. And they may or may not be horizontal, depending on the geology and the attitude of the field. With Poisson's ratio and Young's modulus, we incorporate the information from the core whenever we can, and the ECS data, we do the same sort of thing. The idea is to basically, this is, I guess, the orientation of this and the magnitudes are really the prize for mining geomechanical work. If we look at the vertical stress, and this is from multiple holes, and this is in a normally stressed environment, at 800 meters, we're looking at 22 to 25 MPa. We do convert that to a gradient as required. And then when we look at the maximum horizontal stress, we can see that the calculations are impacted by the geology. And in this particular example, these changes are changes based on changes in lithology and also faulting. We're looking at changes from gneiss to carbonate to amphibolite, material within the interval, and also we're looking at quite a number of faults associated with various episodes of deformation in this particular sequence. But the idea of showing this is that you can actually see stratification in the stress. And this is kind of the same with the minimum horizontal stress. And if I continue on, we're going to talk about a couple of local examples to the Sydney Basin. And here's the first example. Again, we have the borehole image data. And then we have the horizontal stress magnitude calculated from it. Because of the math, we do get flips in hemisphere from one side to the other. And then we have the principal stress, which is plotted here. And again, these stress orientations are calculated here. In this, because this comes from the coal industry, they do log the sonic, the full-wave sonic, so we get both a compression and shear sonic, and they log the neutron and the density. And one of the things environmentally here, they're moving away from logging, they're trying to get away from logging any tool that has anything to do with radioactivity. And in some places around the world, it's prohibited to log density in that kind of environment. This is the normal saturation. Obviously, it's all water bearing. And this is basic lithology sequence through the interval, entering into coal, and then you've got sand underneath. And then we've got the same things. We've got the mechanical properties we've got Poisson's ratio. We've calculated Young's modulus, and we've also included a ratio called GSR, which is geophysical stratigraphic ratio, which is a qualitative measurement. And then here we have the magnitudes of sigma 1, sigma 2, sigma 3, and plotted on top of all this, we've got Poisson's ratio values taken from the overcoring, and we've just plotted those for comparison. This, interestingly enough, is a normalized stress value, and this is normalized to, I think it's about 15 MPa, 16 MPa, and that is a standard value that they use for some of their work here. So they normalize all the measurements to a default UCS strength, I believe, of 16 MPa. And this is example 2. The interval is much shorter. It's the same coal seam. It's higher. Again, we've got a similar sort of thing here. We've got overcoring done just below, and then we've got some overcore measurements up here, and I've got the measurements plotted here on this. Again, we've got the 2 points here, and this is with the 3D overcoring.
Nick, you got 3 minutes left.
Yep. So this is an example of the horizontal stress. The horizontal stress in both is generally slightly northeast-southwest in both. And then we've got the horizontal stress compared with the overcoring. And we've got, comparable matches in 3 of them. And then the 4th one, we've got a bit of difference between the overcoring and the horizontal stress, but generally good agreement. And if we take the sigma 1, in this case, the sigma 1, sigma 2, sigma 3 are very similar to the horizontal stresses, being that they're horizontal. And basically, this is kind of what we do, give them the information for the orientation and the magnitude of the principal stresses. If we plot it in a vertical graph, we've got the same thing here. We've got the coals, and then above and below, because these holes are separated and one is deeper than the other, the trend of the horizontal and the vertical stresses are pretty much the same as you would expect, being deeper. And we also see changes based on lithology and so on, which is interesting. And in the sigma 1 to 3, a similar sort of change in the stresses are here as well. And so for the final slide, we take this information and plot it for the horizontal maximum stress, magnitude, and direction. And that's basically kind of what we do.
Great, thank you. Thank you, Nick, for the great presentation. I think it was really interesting to see what you do. And are there any questions? Yes, Babu. Can't hear you. Here you go.
No, it was just I was trying to clap. That's very good presentation.
Okay. Rita, you raised your hand as well.
Yeah, hi, thank you for the presentation. I just had a question because you were showing how, where you cross faults, you have, you know, some changes in the magnitude of the stress directions. I guess in a normal stress environment, you know, probably most likely what slip direction will be on that fault, you know. But I wonder in like a complex environment, would you be able to use the principal stress orientation? So say you saw a fault on your image log and you don't necessarily know the slip direction. Would you be able to use your principal stress orientation data to figure it out? Thank you.
Yes. Well, to answer your question, I think we can. We've worked on a gold mine that's actually considered a dome, but basically what they did was they drilled horizontal, well, not horizontally, about 50 degrees was the tip of the hole, which is about 40 degrees from vertical deviation as we would know it. So they think of things from horizontal, the angle from horizontal, right? And they drilled this thing through the core of an anticline from one side to the other. And we saw a dramatic change both as you entered the core and as you left the core, because in the center of the core, they also had a different lithology as well. So therefore, from what you're saying, although it's not a similar situation, oh, yes, it is, because that fault, that anticline is sits above a an ancient strike slip fault, a Proterozoic strike slip fault. So yes, you see variations, and they were kind of expecting that in the principal stress, because that was going to impact how they were going to actually develop their mine. They didn't tell me any more. I just worked out, okay, so this is what's happening, and I think you've done this. And they said, yeah, that's correct, that's right. But they didn't want to share any more with me, so but they were very happy. So,
Thank you.